So talking about chromium oxidations. So chromium oxidations are the really harsh oxidations. They're the ones that will keep oxidizing things. They won't stop. So PCC is the one that stops, only does one oxidation, but chromium will oxidize all the hydrogens attached to the carbon bond oxygen. So the first step, mechanism of this I wanted you to know was chromic acid, which is this right here. The first thing it's going to do is actually going to get protonated. So there's H plus in the system. So what that's going to do is make the chromium that much more electrophilic. We need it to be reactive because the chromium is actually going to react with the alcohol that we want to oxidize. So I have a primary alcohol here. So by protonating the chromium, right, I made this, by protonating the oxygen, I made the chromium more electrophilic. Right, the plus charge is here, but really, right, the metal is electron deficient. Right, Lewis dot structures, they can lie to us. So what happens? The oxygen is the nucleophile. It reacts with the chromium. It adds in, it breaks that pi bond. Right, so the oxygen added in, we got to balance our charge, an overall positive charge here. We need to have a positive charge in the next step. So the oxygen lone pair goes there, so we have a plus charge on this oxygen right here. The next step is just a proton transfer. So you don't really need to have a mechanism for this. Essentially what happens is the hydrogen that was on that oxygen is going to be transferred to another one of these OHs. It doesn't matter which one. All right, so again, we balanced our charge. So the hydrogen that was here ends up on this oxygen over there. So that makes. All right, so the next step is going to be we're going to kick out this water. So the electrons between this OH bond, we're going to regenerate the acid essentially. These electrons will come down, and then I'll kick out the water. That's an elimination step, right, that we've seen before, like remaking the C double bond O. C double bond O CR. So following that step, we just regenerated H plus from here, and we kicked out the water. So again, we're going to protonate the oxygen and the chromium. So the lone pair here is going to be the nucleophile, and that's going to react with the H plus to protonate that chromium. So same as that first step, and that's just going to make that chromium just more electrophilic. So similar to what we did before, but now I have a different structure on there because I have the alcohol now attached. You know, at the end of the day, we knew we were trying to remove these hydrogens. That's what the oxidation part is. So the water is going to come in and play and take one of those hydrogens. And that's what's going to give those electrons to that chromium there. That's what's going to first make that oxidize that first bond off. That first CH bond has now been removed. And so now we're with an aldehyde. So I want you to know up to this point. That's all I want you to know up to this point. So the keys that I want you to remember, you protonate the oxygen and the chromium with H plus, right? If there's H plus around, you need to use H plus, right? So the lone pair of the oxygen takes that H plus. That makes the chromium that much more reactive for the alcohol to react with it, right? You do a proton transfer. You get water, which is a good leaving group, right? So you remake the C double bond, CR double bond O. You also make H, so you reprotonate again, and now the water, instead of reacting, right, with the chromium, you're going to use this reactive chromium to get electrons now because it's electron deficient, right, because you protonated it. The oxygen in the water is going to take the H. Those two electrons are going to form a new pi bond. And the bond between the oxygen and the chromium, those electrons are going to go to the chromium now. So then it leaves. Yep. So right. So anytime it's a oxidation reduction reaction, the carbon here got oxidized, right? It lost a CH bond. The chromium got reduced, right? It lost a CO bond or a bond to oxygen, right? This carbon got a bond to oxygen. This chromium lost a bond to oxygen. So this got oxidized. The chromium got reduced, right? At the end of the day, look at chromium's getting electrons. It's getting reduced. It's getting electrons. This carbon's this carbon's more bonds to oxygen is getting oxidized. So this is, I want you to know this first step. Now it keeps reacting, right? This aldehyde and the mechanism you don't need to know. chromium is going to keep reacting with this and turn this finally into a carboxylic acid. Right? It's not going to stop here. If we wanted to stop it here, what would we use? We'd use PCC. But chromium is going to actually turn this into a carboxylic acid. Epoxide regioselectivity. So let's talk about what situations would we need to have nucleophiles react to carbon 1 versus nucleophiles reacting at carbon 2. So first we need to understand if something at carbon 1, is that the more substituted or less substituted side? Less substituted. So we've talked about that being the basic conditions. Right? So basic conditions react at C1. And what does that mean? That means, right, reactive nukes. Right? So what are some examples of reactive nucleophiles? Cyanide, so CN minus, good. Grignards, right? So things with negative charges, right? Reactive nucleophiles, right? A nucleophile is electron rich, so things like anything attached to magnesium bromide, organolithiums, right? Anything with a you could think anything with a negative charge. Deprotonated nitrogens, whatever, right? Reactive nucleophiles. Those things, it's all about sterics. It reacts with carbon 1. If we want to react with carbon 2, we call those acidic conditions, just like they sound, right? Basic, of course, means electron rich, so reactive nucleophiles. Acidic conditions, just the opposite. So we don't want reactive nucleophiles now. Now, essentially, right, just like you imagine, you're looking for, right, acid, H+. So the nucleophile in those cases is not going to be reactive. Right? It's not going to have a negative charge. There's going to be things like H+ around. So what are the ways to get H+? There's HCl, there's H2SO4, right? A lot of times the solvent ends up being the nucleophile in some of these cases, but the hallmark is, look at the charges. What's the, like this one's going to have an overall positive, there's H+ around, acidic conditions, right? Things with negative charge. Now, be careful, I realize, right? A lot of times CN comes as KCN, right? Or Grignards, right? It's find the reactive nucleophile. There's a carbon with a negative charge, right? Is there a nitrogen negative charge, an oxygen with a negative charge, right? You can think of things like that. Those are basic conditions, reactive nucleophiles, sterics. Acidic conditions, the first step in acidic conditions is actually you protonate the epoxide, you protonate the oxygen, make it more reactive, then you have your nucleophile react with carbon 2, the more substituted carbon. Both of these cases get anti-addition, right? You get trans products, but right, different types of reaction conditions get you different regioselectivity, different regions of the epoxide. So this was a test question about carbocation stability. So this is really just kind of probing how well do you understand the 3 ways to stabilize carbocations. So what are the 3 ways to stabilize carbocations, right? They are hyperconjugation, there's pi bond resonance, and then there's lone pair resonance. And those are in order of increasing importance. Right? Hyperconjugation is the least effective. Pi bond resonance, you actually move electrons. Lone pair electrons, you move electrons, and you also usually fulfill the octet rule. So you look at these 5 things, you can see all examples here. Both of these are about hyperconjugation, a tertiary and a secondary. Here's an allylic carbocation, a secondary allylic carbocation that can do pi bond resonance. And then you have these two, which both can do lone pair resonance. Right? So you can draw the lone pairs in here. So off the bat, we know, right, hyperconjugation is the least effective. So we should be able to rank these two versus each other. So which one's going to be the least effective? If it's 1 through 5, 1 being the best, we'd hopefully say this would be 5, this would be 4, right? And then there's 2 lone pair ones, and there's a pi bond one. The pi bond resonance is good, but we never complete the octet rule, so this would be number 3. All right, these two, carbocations next to a lone pair. So now the question is, which one is going to be more effective at sharing electrons, a nitrogen or an oxygen? Who's more likely to share electrons? Nitrogen. Why? It's less electronegative, that's right. So this one is actually going to be more stable, so this would be number 1. And this would be number 2, because a nitrogen is more likely to share electrons than an oxygen. Exactly. Nice. So let's say you have these 2 things. So you have an alcohol you've activated with sulfonyl chloride, the tosyl chloride or mesyl chloride, right? That the SO2ClR group, here's just some methyl. So you've added that to an alcohol to make it a good leaving group. And you're going to react it with an O-, this isopropoxide. So the question is, well, why does this happen, right? So this is an equilibrium reaction, right? So how can we make it go this way? How can we shift it to start? How do we know it goes to products? So let's look at the stability of the two products. So let's look at the product here. It's going to be an SN2 reaction. So the mechanism we should know. And so there that goes. Okay, so we have our products drawn. We did an SN2, so we did an inversion, right? The nucleophile came from the opposite side, so this leaving group was wedged. So the nucleophile is going to end up being hatched, and the methyl group in this case was hatched, ends up being wedged. We did an SN2. And the question is, why are the products favored here? Who can give me a reason why to think about? So I don't look at either of these two things and think they're any much different stability-wise. But if you look at the charge things, what can this charge thing do that this one can't? This one can do resonance. So that's going to help stabilize. That's why this is such a good leaving group, right? Or like an iodine's a leaving group because it's so big, it can stabilize that charge, right? So these leaving groups that have resonance are usually really good, and that's going to help favor the equilibrium and push it towards this way because it's going to be much more stable than an O- that can't do resonance.